Hope that will change again soon. But for now, that's how it is. So I will try to lecture for you remotely. So we were dealing with the Cello theorems. So you have to find chalk which actually works. Okay, we are talking about the Cello theorems. And I wanted to start proving them. So let me start with, I had made some preparations about actions of groups on sets, and now I want to just start the proof of the first Cello theorem. Proof of the first Cello theorem. So I remind you the statement is the following. So if G is a group with G having P to the M times R elements, where P is a prime number and P does not divide R, then the statement is there exists a P Cello subgroup H of G. So that means that it has the maximal power of P that is possible as number of elements. So the number of elements in H is P to the M. Okay, so now we want to prove this. So first I start with an elementary lemma, which is just about counting things. So let S be a set with P to the M times R elements, where we have the same assumption here that P is a prime and P does not divide R. Okay. Prime not dividing R. Then if I look at the subsets, the number of subsets of S of P to the M elements is this binomial coefficient. So I write it N choose P to the M. In different countries, there are different conventions, so I also abbreviate it as N. And to remind you of the notation, this is just N times N minus 1 and so on, times N minus P to the M plus 1 divided by P to the M times P to the M minus 1 until, and so on, until you reach 1. Same number of factors above and below. So this is the standard binomial coefficient. And furthermore, P does not divide. Okay, so the first statement that the number of subsets of a set with this number of elements with P to the M elements is this number is standard. It's almost, that's basically the definition of the binomial coefficient. So therefore, that we know. So we only want to show that P does not divide this number. So that the number of subsets is n is by definition. So we want to show that P does not divide the number. So let's look how this goes. We want to show that P does not divide we just look at it. So we note, so whenever some power P to the L divides the numerator, so the general element here would be called n minus k, and the general element would be P to the m minus k. So whenever P to L divides n minus k in the numerator, the same power P to the L divides the corresponding factor in the denominator. Why is that? So we write k equal to, say, P to the L times S, P not dividing S, then L will be smaller than this number m, because we know because k is smaller than P to the m. No, we only have the factor here minus 1 and so on until minus P to the m plus 1. So, so therefore, n minus k is what is it? M r minus P to the ls, and P to the m minus k, which is P to the m minus P to the ls, are both divisible by P to the L and not by P to the L plus 1. So we see that the maximal power for every factor here, the maximum power of P which divides the factor above is the same as the maximum factor of P that divides the corresponding factor below. So the factors of P precisely cancel, and so this is not divisible by P. So now we want to prove the theorem. Using this. So how would we want to prove this? In some sense, we will find out that all three Cello theorems will be proven by a somewhat clever application of the orbit stabilizer theorem, always with the action of some group on some sets. So in this case, the set that we are looking at will be a set with, will be the set of all subsets of P to the m elements of G. G precisely has as many elements, and it will play a role for us that the number of these sets of P to the m element subsets of G is not divisible by P. This will allow us in the orbit stabilizer theorem to deduce that something else has to be a power of P. Okay, so let's do it. So let S be the set of all subsets of P to the M elements. Okay. So note that by definition, so that's not, now I called it, yeah, now I call this S, but anyway, so before S, here S would be G, no, but now I take here instead S, these subsets. So we decompose S into orbits for the left multiplication. Okay, so we have the left multiplication, G times a subset. So the action G times is just M. So, no. Okay, so we have this. So, so we have, this obviously defines an action. We had seen this also in the previous time. We can decompose this set S into orbits for it. So it's a disjoint union of the orbits. So therefore, the number of elements in S, which is this number n that we had here, is equal to the number of elements in S, which is equal to the sum over all orbits O of G on S for this left multiplication of the number of elements in the orbit. Okay? So that's just the fact that it decomposes into orbits. So we will want to find, so what is our aim? We want to find one orbit which consists of only one element. Then its stabilizer will be forced to have as many elements as we, or no, we at least, so we want to find, yeah, at least an orbit whose number of elements is prime to P, and then we will find that its stabilizer has to be a pseudo subgroup. So P does not divide N. So what was it? P to the M times R, choose P M. As we had seen in the lemma, thus it cannot be that the number of elements in every orbit is a multiple of P. Otherwise, the sum would be multiple of P. So thus there exists an orbit O, which I write as a G of M, so for the action of G on M. So the orbit of a subset M, such that P does not divide the number of elements in this orbit. So by definition, so we had this proposition which was a proposition about the action of by left multiplication on sets, which said that, so for the left multiplication, the number of elements in the stabilizer of a subset U divides the number of elements in U. Okay, so thus we know that for any orbit, the number of elements in the stabilizer of the orbit divides p to the m. So thus, if I take this stabilizer with respect to the step multiplication action of m, divides to the m. On the other hand, we can apply the orbit stabilizer theorem. And what does it say? So it says the number of elements in the group, which is p to the m times r, is equal to the number of elements in the stabilizer of our set M times the number of elements in the orbit. Now, P does not divide G of M. So this does not contain a factor P. So it means that this factor must be divisible by P to the M, because all the factors, the product of these two things is P to the M times R. On the other hand, we also know that it divides P to the M. So the only possibility is that the number of elements in this stabilizer is P to the M. So thus, the M divides M, and thus P to the M is equal to the number of elements in the stabilizer. And so we have found a subgroup of G, namely the stabilizer of the set M, which has P to the M elements, so a P-Pseudo subgroup. Okay, so this is not a super complicated proof, but obviously it comes, it requires some idea. I mean, to do the whole setup, to think of this action on groups and so on is highly non-trivial, so one wouldn't expect to come up with it. On the other hand, the trick is, in the end, rather simple. You just try to find, some action for which there is an element whose orbit has number of elements prime to p, and then it follows that by the orbit stabilizer theorem, the stabilizer of it will be a P-Pseudo subgroup. And also, as I said, the other pseudo theorems are somehow done by the orbit stabilizer theorem in rather similar ways, but always applied in a slightly different setting. So now we want to prove the second pseudo theorem. So the statement here was that all P pseudo subgroups of G are conjugated. That means if H and H prime are P pseudo subgroups, then it follows that I can write H prime equal to A to the minus 1 for some A in G. Now again, this seems a rather difficult statement because somewhere out of nowhere you have to be able to produce this A, which connects these two subgroups. That seems highly unlikely that we can find it somehow. And so again, we try to do it in a similar way by using the orbit stabilizer theorem and finding some orbit which contains only one element, and this will give us what we need. So let's see how this works. So in this case, we will have So let me write it down. So let H and H prime be P pseudo subgroups of G. We want to show, as I said, there exists an element A in G such that H prime is equal to A, H, A to the minus 1. So we will do this now by letting H prime act on the coset space G mod H. So H prime acts on G mod H as follows. So remember, G mod H is just a set of all B times H with B in G. Again, in some sense, just by multiplication, but by multiplication here, it's just by element H prime in H prime will act on BH just by multiplying what we have here. So this is just defined to be H prime BH. Again, some kind of left multiplication. However, we make it act here on these cosets. Okay, this is obvious in action because you can see the product here will correspond to applying it twice, and the trivial element of H prime will do nothing. So this is an action. So again, we can. So we should note that H is a P pseudo subgroup. So therefore, the number of elements here is P to the m R divided by P to the m. So this is R. We have that the number of elements in G mod H is equal to R, particular prime to P. Okay, maybe I remember that because that plays a role. And obviously that is what we want here. So R is prime to P. So if we now decompose G mod H into actions, into orbits under the H prime action, there will be at least one orbit whose number of elements is prime to P. So let me write this through. So thus, there exists at least one orbit. So there exists an orbit. So an H prime orbit, I say, and prime orbit. So H prime AH, so the orbit of some coset AH, and it's not by chance that it's the same A as there, such that the number of elements in this orbit is not divisible by P, so is prime to P. And now we can, again, basically apply the orbit stabilizer theorem. So what is now the stabilizer of AH for this H prime action? So the stabilizer of AH, so this would mean H prime AH, so the stabilizer in H prime of AH is a subgroup of H prime and we know that P to the m, but again by the orbit stabilizer theorem, P to the m, which is the number of elements in H prime, because it was a p-pseudo subgroup, is equal to the number of elements in the stabilizer times the number of elements in the orbit. Now, we know this number is prime to p, so it's not divisible by p. But obviously, it has to be a divisor of p to the m. The only possibility for this is that h prime of AH is equal to 1. Number of elements in A. So the orbit consists only of one element. So the orbit is just AH, and thus the stabilizer has p to the m elements. So as the subgroup of H prime, it follows that H prime of AH. So the stabilizer of H prime of AH in H prime is H prime. Okay. So that essentially does it. Now we just have to put it together. I claim this will mean precisely that this A will do it for us. That H prime is AH A to the minus 1. So for this, we just have to translate this a little bit. So we had that, what was the statement? We had H prime of AH is H prime. So that means thus for all H prime in H prime, we have that, and say all H in H, we have that H prime AH is an element of AH. So now we can multiply here by H prime. So we can multiply first by H from this side. This gets absorbed here, and then by H to the minus 1, and then by A to the minus 1. And so it follows that H prime is an element in A to the minus 1. So in other words, thus we have shown that H prime is contained in A to the minus 1. Now, H was a p-pseudo subgroup, and H prime is a p-pseudo subgroup. So both have the same number of elements. So therefore, if one is contained in the other, they're equal. As both have p to the m elements, they are equal. Okay. So again, here we're using the orbit stabilizer. We somehow, again, singled out an orbit which has number of elements prime to p, and then this again did it for us. And now we come to the third pseudo theorem, which again works in a similar way, only that this time we will use the action on subgroups of G by conjugation. Well, first it has a rather trivial part, which one doesn't really need anything for, and then let's see. Proof of the third pseudo theorem. So let me again also recall what it is. So we had the number of elements in G was still p to the m times r with p prime to r. and let S be the number of P pseudo subgroups of G. We know there's at least one by the first theorem, and then we have two statements. Then S divides R, and S is congruent to 1 mod P. If we divide S by P, the rest is 1. So it's of the form K times P plus 1. Okay, so this is the statement. Now we want to prove it. So the first statement, that S divides R, is essentially trivial if one just spells out what the situation is. But again, using the second Cello theorem. The second Cello theorem says that all P Cello subgroups are conjugated. So therefore, the most natural thing is to look at the action of G on the P Cello subgroups by conjugation and see what that does. So by second Cello theorem, all P Cello subgroups are conjugated. So anyway, thus it follows the number of P Cello subgroups, so S, which is the number of P Cello subgroups, is the orbit of one P, is the number of elements in the orbit of one P Cello subgroup under conjugation. It's equal to the number of elements in the orbit of one subgroup H, so one fixed P subgroup H under conjugation. No, I mean, just to spell it out, you have an action of G on the set of P Cello subgroups of G by sending so G times the P Cello subgroup H is just H G to the minus 1. And this clearly defines an action. And so we know that all the P Cello subgroups form an orbit under this action because they are all conjugated, and so we want to know how many elements are there in the orbit. And this, for this, we can, in some sense, again, use the orbit stabilizer theorem. So we can ask ourselves, what is the stabilizer of our P Cello subgroup for the conjugation action? We know what the stabilizer is for the action because we had it. The stabilizer is just the normalizer. So for the stabilizer, of H for the conjugation action is the normalizer, NH. Okay. So it follows that this number S is equal to the number of elements in the orbit which is the index of the stabilizer in G. So S is equal to the index of NH in G, again by orbit stabilizer theorem, or whatever, or something we proved in preparation to that theorem. So we know that H is a subgroup of NH, and NH is a subgroup of G. Actually, so we therefore get, thus it follows, that the index of NH in G divides the index of H in G. Now, if you spell it out, we have that the number of elements in G is equal to this and this is equal K and so it's equal to the number of G in H times index of in NH. H times H. And then you can just reshuffle this. And so you can put this together. And this is the index of H in G. So you can see it divides it. Okay, anyway, I didn't need to do it like that, but it's anyway clear. So, and recall that, this is the proof because the index of H in G is R. Because H was a P pseudo subgroup, so it has P to the M elements, so the index is precisely the rest. Okay, so this first part is therefore in some sense essentially trivial. You just apply the definitions and you see it has to the number of P pseudo subgroups has to divide the number of elements in the has to divide this number R. Now the first part is also not much more difficult, but we have to at least one has to again find some nice action where again one wants to find a special element which whose orbit consists only of one element, and from this one the statement will follow. So we precisely want to find an action of something on these P pseudo subgroups such that the group which acts has P to the M has a power of P as elements, and there's one orbit which has only one element, so therefore and all the other orbits have the number of elements in the orbit divisible by P, so the total number of P pseudo subgroups must be congruent 1 mod P. So let's do this. So where is it? Okay. So we want to show S is congruent to 1 mod P. So we denote by S the set of P pseudo subgroups, so H1 until HS, the P pseudo subgroups of S. And the first one I want to take is our original our original H. So we had viewed the P0 subgroups as the orbit of one element under conjugation. So we take this as the first one here. So now again, we want to decompose S into actions under conjugation, but not under the whole group G, because under the whole group G, there's only one orbit, but under a smaller group, namely just under conjugation by H itself. So decompose S into orbits under the action of H on S by conjugation. So that just means, again, we have, if I take H times one of these HI, this is just H, so this is just H, HI to the -1, and this will be possibly another one. So now I want to claim there's precisely one orbit which consists only of one element. So it's clear that there's at least one orbit which consists only of one element, because if we take H, its orbit only consists of H itself. If we conjugate H with an element of H, we stay in H. So clearly, the orbit of H under this conjugation action is just H. So that consists only of one element. So we want to claim that all other orbits consists of more than one element. So now let HI consist of a single, so let the orbit of HI of a single element. So that means that the stabilizer of HI inside H is the whole of H. I take H of HI for this conjugation action. This is equal to H. But we know what the stabilizer is. The stabilizer for the conjugation action is the normalizer. So therefore, consists of but H of HI. No. Okay. So this is this, but so this is some. So what does it mean? So that means all the elements of H should act trivially on HI by conjugation. So we know what the elements in G are, which act trivially. Namely, these are precisely the elements in the normalizer, because the stabilizer inside G for this action is the normalizer of HI. So therefore, this stabilizer here is equal to the whole of H if and only if H is contained in the normalizer. Then H contained in the normalizer of H in G. of HI. So H is a subgroup in the normalizer of HI. HI is also a subgroup in the normalizer of HI, and we even know that HI is a normal subgroup in the normalizer. Because that is what we mean. So we have that H is a subgroup of N of HI, and HI is a normal subgroup. In N of HI. And obviously, both H and HI have P to the M elements. So they are both Cello subgroups of G, but they are also therefore also Cello subgroups of N of HI, because the largest power of P that divides N of HI can at most be smaller, is smaller or equal to M, and we have such a subgroup, so it must be equal to M. So they both have P to the M elements, so thus they are Cello subgroups of N of HI. But now we have two Cello subgroups, H and HI, of this N of HI. We know, and one of them is normal. We know that all P Cello subgroups must be conjugated. If one of them is normal, then both of them must be equal, because if I conjugate this one, it goes to itself. So thus, H is equal to HI. Okay, and so we find, after all this effort, that there is a unique orbit for this action of H on the P Cello subgroups, which consists of only one element. So thus, H1 equal H is the unique element in S with H of HI is equal, the number of elements is equal to 1. But now we can again use the orbit stabilizer theorem. So by the number of elements in H is equal to the number of elements in the orbit times the number of elements in the stabilizer, we see that, and so this number is P to the M, we see that the number of elements in the orbit must always be a power of P. Positive power of P for all I different from 1. So when H is different from HI, H1. When I is different from H. So thus, we have one orbit which contains one element. All the other elements have number of elements divisible by P. So it follows that the number of elements in S is congruent to 1 mod P. Okay, so this was, so maybe I write it out. S equal to the number of elements in S, which is equal to the sum over all orbits H of I, the number of elements in H of Hi, and this is congruent to 1 mod p. Because all of these numbers except for 1 are divisible by p, and one of them is equal to 1. Okay, so this was as much as I wanted to say about these Cello theorems, and therefore also about groups so far. So I don't know whether there are any questions now. So this kind of, so as you can see, the Cello theorems were a little bit more advanced than the rest of the group theory part, because we really put things together and we apply them, in particular what you have learned about actions of groups in a somewhat non-trivial way and combine things. But okay, so this was one of the reasons why I introduced them, so that one can see that one can also do something a little bit more interesting. Obviously, there are much more interesting things in group theory. So now I would want to go to the next chapter, which is about rings. And here again, we will start from 0. So I will just introduce to you what a ring is and show some basic properties like we did with groups and introduce some examples. And so we really start again by 0. And in some sense, I think this chapter is is altogether more elementary than the one on groups. In particular, there's no real high point like the Cello theorems. But one of the reasons we do it, that anyway, to learn some, it's the basis that one needs for commutative algebra and therefore for algebraic geometry later. And also it is partially preparation for the last part of the lecture on Galois theory, which will be a little bit deeper. So, so now we would talk about rings. So first I have to tell you what a ring is. In some sense, everybody knows it. In a group, we have one operation. We can multiply elements. And we have some basic law like associativity and the inverse and the neutral element. For a ring, we have two operations, addition and multiplication. We want that the addition is commutative and both are associative, as one always requires. And then we will have a basic compatibility, which is given by the distributive law. So let me write this down. And so maybe as a basic example of rings, the simplest example would always be the integers. You can add and multiply integers. You cannot necessarily divide them. So let me do the definition. So a ring R is a non-empty set with two binary operations. So one is the addition. So no, A comma B is sent to A plus B, which is we call the addition. And the multiplication from R times R to R, AB sent to A times B, or just as before written AB, the multiplication. And we want a few laws about this. The first one, so first we have one more thing. We have one distinguished element. Then we want R to be, with addition, to be a group, actually a commutative group. So we have to have a distinguished element, a neutral element. So, and a distinguished element zero in R, such that first we want that if I take R with the addition, this is an abelian group with neutral element 0. Okay, so like in the integers with addition are an abelian group. And then for the multiplication, we require much more. We assume we require the associative law. A times B times C. And now there's no connection between addition and multiplication. That's maybe not so great. So we have a basic compatibility, which is the distributive law. Which says that if I take A times B plus C, this is equal to AB plus AC. And as I have in the moment not assumed that multiplication is commutative, we also have to require it the other way around, namely B plus C times A is equal to BA plus C. And that's all. So as I said, an example is the integers with the addition and the multiplication. Obviously, the neutral element is 0. So we have an abelian group, we have a multiplication, which is associative, and we have a distributive law which ties these two things together. So just, it's not very important, but just as a remark, a simple reformulation of the distributive law. So we can reformulate the distributive law as follows. So distributive laws say that if I take, say, the left translation by an element A, so from R to R, which sends B to A times B, this is a group homomorphism for R with addition. No, because that's just what it says. If I take A, if I take A times B plus C, this is A times B plus A plus C, plus A times B plus A times C. And in the same way, obviously, the right multiplication with A maps to BA is a group homomorphism for R. This also, again, says in some way that there is some compatibility between addition and multiplication. That's what the distributive law says. Okay. So as with groups, we can also look at subrings. So for groups, you have subgroups. For rings, you have subrings. So a subgroup of a group is a subset with the operations, with the multiplication in the group restricted to it becomes a group. And the same for a ring, if you take both operations. I write this in a slightly different way, which is equivalent definition. A subring A of a ring R subset A in R such that first A with the addition is a subgroup of R with addition. And the multiplication inside A does not leave A. So, and for small a and b in A, we have A times B is also in A. And this then obviously implies that A, with the restriction of the addition and the multiplication, becomes itself a ring. So a stupid example would be if I take 2z, set of all 2n and in z, 2n and in z is a subring of z. No, because if I add two even numbers, I get an even number. And anyway, it's certainly we already knew it's a subgroup of this thing with addition. And if I multiply two even numbers, the number will also be even. So, so in the moment we have just rings. We will later usually look at better examples for ring for which more properties hold, nicer properties. One nice property that a ring can have is that it's commutative. So we have assumed in the definition of a ring that the addition is multiplicative, is commutative. So for a ring to be commutative means that also the multiplication is commutative. And many examples of rings that we know are commutative, for instance, the integers are. So definition. The ring R is commutative if A, B is equal to B, A, all A and B in R. That, as I said, if and only if the multiplication is commutative. We already know that the addition is, so that would not be a condition. So now if you have a ring does not necessarily have to have a neutral element for multiplication. For instance, 2z doesn't have it. You know, it doesn't happen that if I multiply an integer by 2, I get the same integer. I mean, unless it's 0, but it doesn't happen. I mean, there's no even number by which I can multiply all integers so that I get the same. But it is a nice property a ring can have. For instance, the integers have it. And so such a thing, such a ring with this property would be called a unital ring. So definition. An element, which I will denote 1 in R, and they require that 1 is not equal to 0, because if I would allow 1 being equal to 0, then somehow the whole thing would be trivial in a very uninteresting way. Is called a unit element. The name is unit element. Later, in a moment, we also get unit, which is something slightly different. If it's the neutral element for multiplication, if A times 1 is equal to 1 times A is equal to A for all A in R. Okay, it's a neutral element for multiplication. And a ring which contains such a unit element is called a unital ring or a ring with 1. So as you can see in this part on rings, we start with just having very many definitions, very many notations, and don't do almost anything with it for the moment, because it's just, you know, the language, the words that we have to introduce, and the basic properties that we are dealing with. So It's only later that one can do something once one knows the words. So a ring R. So if R contains a unit element, it is called a unital ring. Or I usually just write a ring with 1. So in the course, we will mostly study commutative rings with 1. So for instance, an example for that are the integers. Okay, now I wanted to give a few examples. So obviously, Z, the integers, Q, the rational numbers, R, the real numbers, and C, the complex numbers, are commutative rings with 1. So one other example, which comes from this, slightly more complicated, is Zi. So this is the set of all n plus mi, where I is the complex unit in the complex numbers. So if you want e to the pi I halves. Anyway, that's a bit, anyway, so what you know as I with n and m in Z. So if you view the complex numbers as a plane, these are just the lattice points where all the coordinates are integers. So, and this is a subring. So this is called the ring of Gaussian integers. Pronounce that, or Gaussian. I write it nicer. Gaussian, after Gauss, obviously, integers. And this is a subring. The complex numbers. So if you multiply any two such things, you know how one, or add any two such things, you will still get that it is a plus bi, where a and b are integers. So these are both commutative rings. And then we also have a non-commutative ring, which is matrices. For instance, we can look at the 2 times 2 matrices, coefficients in R as an example. So this would be the set of all matrices A, B, C, D, where A, B, and C and D are real numbers. And this is a ring with matrix addition and multiplication. Now you know how to add matrices, just you add the corresponding elements, and the matrix multiplication you also learn. And you can see that it's easy to see that this is a ring. You have the associative law and the distributive law, but it's also non-commutative. So this is unital ring. Obviously, the neutral element is the matrix 1, 0, 0, 1, which is non-commutative. Okay, so maybe was this all examples that I wanted. Well, maybe just one more, as we had it also in the group theory chapter. We can also again look at our zk, so the integers from 1 to k with this addition that we had. So if we take zk, was set 0, 1 to k minus 1, so for k in z. Is ring. So via, we had seen the addition was that if I take element n plus m in this ring, this would be, I take the sum in z and I take the rest. So this is sum in z. This is the rest dividing by k. And in the same way, we can also multiply n times m is equal to the rest of n times m, where this is the multiplication. And you can easily check that this defines a ring. So we have a ring structure here. And maybe also just list as a remark some trivial properties which are similar to what I stated for groups. So maybe even for some, so if R is a ring, A and B are some elements in R, then I can say some simple things. For instance, if I multiply A times the element 0 in the ring, it will be always 0. And if I multiply minus A by minus B, this will be, or say minus A times B, this will be equal to A times minus B. So obviously minus A is the inverse of A for the addition, and this is equal to minus of the product AB. And minus A times minus B is equal to AB. And if R is unital, if I take the additive inverse of 1 and multiply it by A, this is A times minus 1. This is the additive inverse of A. So these are these points. Okay, I will not prove it. These are all trivialities. No, it's a very simple exercise to check these things. I think here it's something like A times 0 is the same as A times 0 plus 0, which is the same as A times 0 plus A times 0. And then you can subtract A times 0, and you get A times 0 is equal to 0. And the other ones are of similar difficulty. Anyway. Well, maybe I don't do that here. Okay. So let me see what I can do now. Yeah, so I want just to introduce a couple of further properties, and I think then my time will soon be out. So again, we can. So one property that the integers have, that not all rings have to have, is that if you have two non-zero elements in the integers, the product will never be 0. So that one can say as saying that the integers do not contain 0 divisors. And that turns out to be a very nice property, and so therefore we will introduce it and we'll use it sometimes. So definition. So let R be a commutative ring with 1. One doesn't really need that, but I will never use it in other contexts. So an element A in R, which is not the 0 element, is called a 0 divisor. If there exists another non-zero element such that A times B is equal to 0. We had seen here that if we multiply anything by 0, we get 0. But if there's no other way to get 0, then we say the ring doesn't contain 0 divisors. So a commutative ring with 1 with no 0 divisors is called integral domain. Integral domain somehow reminds us of the integers. So as an example, we have that if we take z with the usual addition and multiplication, this is an integral domain. We know that we cannot get 0 by multiplying two non-zero numbers in the integers. On the other hand, we can look, say, at Z6. So if we look there, if we take, for instance, we multiply 2 times 3, this is the rest of 6 under dividing by 6, so this is 0. So this, and neither 2 nor 3 are 0. So that means Z6 is not an integral domain. But we could ask ourselves when such a thing will be an integral domain. And so if P is a prime number, then if n and m are both not divisible by p, then n times m is not divisible by p. So that if n is not 0 in Zp, and m is not 0 in Zp, then n times m is also not 0 in Zp. So thus, Zp is an integral domain. Actually, if you think of this example, it's quite obvious that Zn will be an integral domain if and only if n is a prime number. Okay. So one of the reasons why integral domains are nice is that one can cancel factors. With an identity, things are equal, and you can divide it by, and it's a multiple of something, then it's also still an identity if you cancel that factor. So this is remark cancellation. So let R be an integral domain. So if, say, AB is equal to AC in R with A different from 0, then B is equal to C. Okay, and this follows just because AB is equal to AC is the same as saying that A times B minus C is equal to 0. So thus, if A is non-zero, then B minus C is 0. Okay, that's also very simple. Now I think the last thing, maybe we'll see, maybe the last thing I will introduce, or maybe there's something more, will be units. So a unit, so if I have a ring with 1, so a unital ring, then the units will be the elements which are invertible. You know, in a group, every non-zero element, every element is invertible for the multiplication in the group. But in a ring, the multiplication will not in general be a group. So, so some elements might be invertible and some elements might not be invertible. So the elements which are invertible for the multiplication are called units. And the units themselves, the set of all units form a group under multiplication, which will be called the multiplicative group of the ring. So definition. So let R be a ring with 1. An element A in R is called a unit if it's invertible for the multiplication, so it has a multiplicative inverse. So if there exists an element B in R with A times B is equal to B times A is equal to 1. So the set of units in R is called the multiplicative group. Of R, and usually denoted R star. So, I mean, in particular, I claim that this is so as an exercise, it's basically trivial. R star with a multiplication is a group. So, I mean, that's, as I said, basically obvious. We know that the multiplication is associative. We know that R star contains a neutral element, namely the neutral element of R, and it has an inverse element for any element in it. That's the definition of a unit. And then finally, if I take the product of any two units, then A times B to the minus 1 is B to the minus 1 times A to the minus 1. So if you have a product of two units, it's also a unit. So we have a group. Let's see whether I have some. I could give just a couple of examples. So for instance, in Z, so, or maybe if I just take the units in Z, just 1 and minus 1. No, the only elements which are invertible for the multiplication are 1 and minus 1. Minus 1 squared is 1. And obviously, these form a group. Then if we look at these Gaussian integers, then I claim the units are just 1, minus 1, I, and minus I. And check this. It's quite simple. I mean, you can certainly see that all of these are units. No, one is a neutral element. Minus 1 times minus 1 is 1. I times minus I is 1. And so you can see they are all units. And conversely, to see that these are all the units, well, you have to think a little bit, but it's not very difficult. Okay. So maybe it's not the right moment to start something new now. So next, I will introduce polynomial rings. So it's a kind of, maybe in some sense, the most important example of a ring, or rather of a construction, how out of a ring you make a bigger ring, to look at the ring of polynomials in a variable x with coefficients in our given ring R. And then we will study this and and see where we go. Okay, so thank you very much. That was all I wanted to say for now. Are there some more questions? Can you actually, I hope you are still all at least hearing me. Yeah, okay. So I hope it's more or less clear. So you can see what I did about rings is very easy. So therefore, I went a little bit fast. So it's just all these definitions and trivial remarks. And slowly we will come to more interesting things. But still, maybe if I went too fast on something, you can also ask me. Okay, so there are no questions. So then I will wish you a nice evening. I hope we will soon be able to see each other again also in person. But okay, for now, I at least hope everybody could see me well. So, and could read well what's written on the blackboard. I mean, if there's any complaint, you should do it so that I can change my ways. Okay. Okay, have a nice evening again, and we see each other on Friday.